video. In today's video, we are going to be focusing on reaction mechanisms. So rather than just looking at a balanced chemical equation to take a look at what my reactants are and what my products are, we're going to break that down into the individual elementary steps in which a chemical reaction takes place, and then we're going to be able to analyze those in order to be able to determine the rate law of a chemical reaction. I'm really excited to get into this today, so let's get started. So with our student learning objectives today, we should be able to analyze a reaction mechanism to determine an overall balanced chemical reaction, identify intermediates and catalysts, write out a rate law based on the slow step of a reaction, whether it is first or not first, draw out a reaction energy profile for a multi-step reaction, explain the function of a catalyst, understanding that the amount of catalyst does not change, and explain ways that catalysts speed up chemical reactions. So let's talk a little bit about reaction mechanisms, and we dove into this a little bit in our last video when we talked about elementary steps. Most reactions don't react exactly like a balanced chemical equation. What a balanced chemical equation does is really just tell you what your reactants are and what your products are, but it really doesn't tell you the individual steps and how to go from reactant to product. Well, reaction mechanisms show those elementary steps that convert our reactants into our products. Now, combining those elementary steps should produce a balanced chemical equation. Well, what do I mean by that? Well, let's look at our reaction mechanism on the right side, which is in blue, and our balanced chemical equation, which is in black. So notice that we have things on the left side, we have things on the right side. Well, anything that is on the right side of the equation in one step that's on the left side of the other can cancel. So for example, N2O2 is going to cancel from our right side and our left side. So you notice that does not appear in our balanced chemical equation. If I look at my second and third equation, I have N2O on the right side and N2O on the left side. Those will cancel. Both my two NOs and two H2s are left over on the left side, and my two H2Os and N2 are left on my right side. So we would combine those, and when we combine those, we get our balanced chemical equation at the top. So it's fairly straightforward to go through and balance these out. Now, intermediates are the term that we use to describe compounds that are produced in one step and used up in a subsequent step. So for example, in between steps 1 and 2, we would say that N2O2 is an intermediate because it's used in the subsequent step and made in a previous step. And we would also argue the same for N2O between the second and third step. Catalysts appear to start the reaction but end up as a product at the end. So they are on opposite sides of the equation, so they would cancel and would not appear in a balanced chemical equation, but they are identified in kind of the opposite way you would identify an intermediate. An intermediate ends one step and begins the next one, where a catalyst starts the first step and you get it back out the second step. Now, again, we go through, we cancel out what are intermediates, we cancel out what our catalysts are, and then combine what is left over to make our balanced chemical equation. So we can actually determine rate laws from our reaction mechanism. So there are really two ways to do this. And what you'll notice is that when we have a reaction mechanism, a lot of times the steps are going to be labeled either slow or fast. If you think about a reaction, the reaction is only going to occur as fast as its slowest step, right? A relay race is, when relay runners run a race, they are only as fast as the slowest person that is running. So if we think about this and utilize that concept and apply it to our reaction mechanism, we can easily write out a rate law. The slow step is always the rate determining step. So if our first step is slow, we use the coefficients of our first step. We use the coefficients and reactants of our first step, and we write that out as our rate law. So in this example here, what would the rate law be for this reaction mechanism? Identify any intermediates. Well, the very first thing I'm going to do is look for my slow step, which is the first step. So I notice that NO2 plus NO2, so my rate law is going to read that rate equals K times the concentration of NO2 squared, because there are two of them. Furthermore, we would consider NO3 an intermediate because that is something that is produced in the first elementary step and then is used up again in the subsequent step. One thing to notice here, notice the difference between the rate and the overall reaction. They do not have to be the same, all right? So it's really important that if you are given elementary steps in a reaction mechanism, that you utilize this method to determine the rate law. So again, just look for that slow step. If it's the first step, just imagine that that's your chemical equation that you're going to use. figure out what your reactants are, and write your rate law based upon those reactants. It's very important that we know how to go through and complete this. If our first step is not rate limiting, thus it says that it's fast, we're going to start with the slow step rate law. So we would write out our slow step rate law. So in this example here, we'll write it out here in just a minute. We would replace then any intermediate with what formed it in the previous step, because the fast step occurs so much faster than the slow step that we can say that those reactants of that step are instantaneously converted to product. So we're going to utilize those in our rate law. So essentially what we're going to do is we're going to substitute NO squared for N2O2. Intermediates cannot be part of your reaction mechanism because they are not formed until the reaction has already started. So we're going to substitute in our intermediate for whatever formed that intermediate. And we can do this because the fast step happens significantly faster than the slow step, so we can make this steady state approximation. So what would the rate law be for this reaction mechanism? Is write out the rate law for that slow step. So rate equals K times N2O2 times H2, but I'm going to substitute in NO squared for N2O2 because that reaction step happens so quickly compared to the slow step that I can approximate that. So my rate's going to be K times NO squared times H2. Okay, so my rate's going to be K times the concentration of NO squared times the concentration of hydrogen. So again, we're going to approximate that step by getting rid of the intermediate and substituting the intermediate for whatever formed it. I go back and check and recognize that, yes, this is an appropriate reaction mechanism for this reaction. And again, also notice that it is not the same as if you were to go through and do the steps with the balanced chemical equation. Another thing we can take a look at is our reaction energy diagrams. And if we know which steps are fast and which are slow, we can represent this with activation energies in a reaction diagram. If you think about it, steps that are slower are more than likely going to require more energy to overcome the activation energy. So we can show this if we know which step is slow and which step is fast. So if I look at the graph here on the right, the first step is our rate determining step. It is our slowest step because look at the activation energy that's required. Remember, the activation energy is from our reactants to the peak. Notice that the second step reactants and the peak is much smaller than that compared to the very first step. That would indicate that that is a fast step when compared to the slow step. So we can take this information and actually draw out a reaction energy diagram or utilize the reaction energy diagram to identify which step is slow and then be able to write out the rate law based on that information. Now, catalysts speed up the rate of a reaction by either increasing the number of collisions or creating a reaction mechanism that is different steps with a lower activation energy. One thing to keep in mind is that catalyst concentration doesn't change because if you remember we talked about previously, catalysts start a reaction, but then they end up as a product at the end of a subsequent step. So if I look at the example here on the right-hand side, I notice that I start with chlorine, but I end with chlorine as well. So that would be representative of a catalyst in this particular chemical reaction. Now, we can draw out reaction energy diagrams that show the change of the activation energy in the presence of a catalyst. Remember that catalysts speed up reactions by either increasing the number of collisions or finding a reaction mechanism with a lower activation energy. Either way, we can represent this with a lower activation energy, a lower hump, if you will, in the center of this graph. Notice that where my reactants start and where my products end are exactly the same. It does not change the amount of energy present in a reactant or product, but rather it changes the amount of energy required to go from reactant to product. So the only difference you're going to see is the height in which the activation energy is if there was a catalyst present or if there was not a catalyst present, just like what you see in the graph here. Hey, I hope you enjoyed the video. Hopefully you learned how to write reaction mechanisms, understand how to identify intermediate, slow step, fast step, reaction energy profiles for multi-step reactions, and how catalysts work, why they're not used, and ways that they speed up chemical reactions. Hope you have a great day. This finishes up this unit. Make sure you like, comment, and subscribe, and we will see you very, very soon in the next video. Have a great day. We'll talk to you later. Bye-bye.